Welcome to Embedded Internals. This is third episode of our series, that is Pointer Thinking series. Pointer Dereference Internals. In this episode, we are going from dereferencing a pointer to compiler, assembly, CPU registers, cache, RAM, memory buses. This is where pointers stop being syntax and becoming hardware. So when we are saying dereferencing, let us take an example. We have integer x which has a value 10 and ptr is a pointer to integer which is storing the address of. So the representation of same inside memory will be address 1000 value 10 corresponding to x. Here corresponding to ptr some address that is 2000 and value it stored is address of. So ptr will be address of x, that is 1000. So ptr is 1000. When we are trying to dereference the ptr, means go to this address and read the value present in that address. So it doesn't mean read pointer itself, read what pointer pointing to. So it is like ptr, this has this address, so go to this address and read the value present in that address. So this is what we mean by dereferencing. So without dereference, we only have address, not the value. So what will be the hardware view of this? So in assembly, it is like load ptr. So address which is stored at ptr into a register, that is rax register, and load that rax register. So whatever is stored at that rax register which contain the address of ptr. So 1000 address of x, load that, read that location and load the value. So rbx will contain, in this case rbx will contain 10 and rax will contain address of pointer. So address of x, that is 1000. So it is like read pointer, get address, read memory at that address. This is what is dereferencing. As we know that any variable name get disappeared after the compilation stage, CPU only knows address. So all the talking after the compilation stage is being done in the address form. So we can say dereferencing requires two reads. One read the address, second read the value. Read address, second is read value stored at that address. So what happened during dereferencing? So at the CPU level, first we will load the pointer and after loading we will obtain the address. So the pointer address is stored is 1000. So taken the same an example, and after that it will request for the memory and send this address through the address bus to the memory. So memory returns the data using the database. So add cut to the memory. So memory returns the data using the data bus. CPU places that data into the register. So this is what happens at the CPU level. Whereas when we are seeing this same as a register level, so we are doing move whatever value memory at the pointer. So whatever value ptr store, move that value into rax register, and whatever value stored in rax register, move that value to the rbx register. So rax register will be memory of ptr. So value stored at ptr is 1000. So memory of ptr is 10. So rbx will have the memory of rax, that is 10,000. So value stored at this location 10,000 is 10. So we will get the value, rbx will have the value 10. So RAX has this 1000 and RBX has value stored at 1000, that is 10. So this is what happening at the CPU and register level. Simply load the pointer, obtain the address, issue the memory request, and that is send that address using the address bus to the memory. Memory will return the data using the data bus, and CPU will place the data into the register. So the communication between CPU and RAM is through it is address and data bus. Address bus from CPU to RAM, from RAM to CPU, data bus. And for the computation between CPU to RAM, we have registers. Communication using bus and computation using registers. So it is like RAM, register, ALU. In the modern system, CPU rarely reads directly from RAM. We have cache in between. It reads from cache. So this is CPU. We have L1 cache, L2 cache, L3 cache, and RAM. So communication happens between CPU and cache. It rarely communicates directly to RAM. So when we are doing dereferencing this pointer variable, it will first check, CPU will first check L1 cache. If hit data found, well and good, it will take 1 to 4. First data found, maybe it will take 1 to 4 cycles. If we didn't find the data in L1 cache, it will move to L2 cache. May require more cycle. And if L2 cache miss happens, then L3 cache, which may require more cycles. And finally, if we didn't find the data into the cache, then we read data from the RAM, which requires multi more cycles. So this will be slower, and this is the fastest. Real memory read path. So when we are dereferencing a pointer, we get the pointer address, which is actually a virtual address. Using MMU and TLB, we translate that virtual address into physical address. And after we get the address real read path. So when we are trying to dereference PTR, means we are getting the pointer address, and that address is a virtual address. So we need MMU and TLB translation. TLB is basically used for optimization. So when we get the address, translated address in our page table, then TLB return that mapping. If we don't have the mapping, then MMU will do the mapping, and then we get the physical address. Once we get the physical address, which is the real address, we will have cache lookup. We have 3 caches, L1, L2, and L3 cache. If we forget the data inside L1 cache, this will be the fastest processing. If L1 cache mesh, then L2 cache. If we didn't find the data here also, then L3 cache. And if we didn't find the data in our cache, then we go to RAM. Once we get the data, then we return or store the data inside the register. So this is the real memory read path. So this is all what is happening when we are trying to dereference a variable. All these things happens in nanosecond. This is the reason we didn't realize. Now comes the common mistake which beginners make. First is null point access. Null pointer means address 0 into 0. So when we are trying to dereference this address, which is an invalid address, we will get the segmentation fault. The second mistake which usually beginners make is trying to update the wild pointer. Wild pointer means we have a pointer. This does not pointing to any valid location, means it is reading from any random location. When we are reading the data from any random location, or when we are trying to do any dereference the random location, that memory address can be valid, invalid, kernel address, or any secure address. And this is the reason we will get the undefined behavior. The value which we get might not be expected. Third common mistake is dangling pointer. Dangling pointer occurs when we don't have the ownership of that pointer. Like we have declared a local variable x and we have stored that address of x into our pointer. Once the function scope ends, so this function, this x, scope of this variable x is inside this function only. Once we return from this function, the scope of this variable got lost. So we lost the ownership of this pointer as well. And when we try to access this pointer anywhere else in the program, we will have the undefined behavior, because we might have the valid pointer, but we don't have ownership to that pointer. This is the reason we have undefined behavior. Now comes the double dereference. Like for example, we have an variable x which has a value 10. We have one pointer p. We have one double pointer q. So p contain the address of x, whereas q contain the address of p. So in the memory location, it will be like q has some address like 3000. It contain the address of p. So that is 2000 address of p. So address of p contain the address of x, that is 1000, and address of x contain the value. So double dereference means triple read. First time we are reading the address of value stored in q, then value stored in p, then value stored in x. So it is triple read. Similarly, multiple hop. When we have triple reference, then we have 4 reads. So it is like multiple hopping. Now the question comes, why dereference is expensive? When we have to do any computation on any local variable, simple variable like x plus y, only the registers are involved. Whereas when we have to do the computation or dereferencing any pointer, then we have to do the address resolution, and after the virtual address is being converted into the physical address with the help of MMU and address result and translation look aside buffer TLB, then with the we get the physical address, and with the physical address we will have cache lookup L1, L2, L3, and once the cache miss happen, then we will possibly read the RAM, and after the RAM translation or computation happens, and we store the value into the register and do the computation. So this is very slow. An embedded system view, we have defined a variable GPIO out, and this points to an register. This is not any RAM register but an hardware register. So we are direct with the help of deref pointers, we are directly reading this hardware register, and if there is any change in the value, we are dereferencing this register and reading the value 1 or 0. Based on that value, we will doing the computation. So we are directly mapping the hardware register into the memory, and this becomes the base concept for MMIO. This is a very simple program where we have declared a variable x having the value 10 and a pointer p, which is a pointer to integer, which stored the address of x, and printed the address and value pointed by that address using the printf statement. Value is 10 and address is stack address. So this all happens in jiffies, but what is actually happening is multi-process. Complete journey of dereferencing of pointer variable will be for a small program like int x is equal to 10 and int p is equal to address of x, and when we are trying to dereference p, that will result into 10. So this will be the complete journey of dereferencing. So in the source code we have used the variable x. At the compiler level, this variable name like x or any label we give will disappear. Only the address will exist. So x will convert it into this address or any random address. This is an virtual. So this address will be loaded by the pointer. So pointer will have p will have the address 1000, and This address is a virtual address, like we have seen in our example. That virtual address will go through the TLB lookup. There we have page tables. If page table mapping will be found, then okay. Otherwise, we will have to do the MMU translation. So a new mapping will, page fault will be generated and mapping will be created by the kernel. And after that, we will get the physical address, which is any address like 1234, which is the real address. So once we have the real address, we will send that address using the address bus. Before the RAM, we have cache checks. We have L1, L2 and L3 caches. So variable will be found in these caches. If we find that in L1 cache fastest, we will data return CPU register, we will print the statement. If not in L1, then L2, then L3. If we miss all the caches, a variable is missed in all the caches, then we will have to do the RAM access. After we read the value from the RAM, data is returned using the data bus. So data is returned and stored in the CPU, and then printf print the value. So all these things happening when we are trying to dereference our pointer. So in this episode we have seen pointer stores addresses. Dereference means follow address. CPU loads pointer. MMU translates address. Cache is searched. RAM access if needed. Data returned to register using data bus. And this is how CPU get back the value. An invalid access causes crashes. We have seen null pointer access, while pointer and a dangling pointer, how they can cause undefined behavior and segmentation fault when not handled properly. And dereferencing is hardware assisted memory navigation. So we can say pointer to address, pointer, we get the address, then memory translation, then cache or RAM, and then we get finally value. This is all in this episode. In the next episode, we will cover pointer arithmetic internals in details. Stay tuned for same. Thank you.